Okay. Part 4 of this lesson that went on forever. I checked my notes from last year and our regular AP Calc class that didn't have COVID to deal with. That lesson was a full period and went over a little bit into the second period. That was a 2-day lesson. So I was a little bit wrong about my goals yesterday about getting through this very quickly. It did take some time, even for a class that, you know, their background was different because of lack of COVID. But this tidies it up, and I really think everything I got to do this morning, I hope you're going to be like, oh, it's mostly new stuff, but I think you're going to go, oh, that's pretty straightforward. The end behavior of complicated functions can often be modeled using a simpler function. They'll give you something crazy. I'm going to do some crazy functions in a minute, and we're going to simplify it down and go, oh, yeah, but that thing would have the same end behavior as this one. You know, and we just compare it to something else. And they start off with a really easy one. They say, use a calculator to show that the function g at x equals 2x cubed can be used to model the end behavior of f at x equals 2x cubed minus 7x squared plus 5x minus 1. And what they're trying to say is, use your calculator to confirm that the end behavior of this one is the same end behavior as this one. And that might be obvious as heck, but when I go to some other examples, it won't be quite so obvious. So this is like getting the feel for what I'm talking about here. So we need that awesome calculator of yours. Let me just find it in here. Oh, I got to go on the H drive. Documents. There it is. Not that. This one. And this one. Okay, here we go. Casio calculator. Now, the graph function will do this question for you. You could get the two graphs on the screen, you could follow them out, and that would work fine. I like the table of values better for limits. The table of values, I can really see what's happening. So what I'm going to do is I'm going to go menu, and I'm going to go into table, not graph. So menu 7. And it asks me for the two functions I want, and I'm going to go 2x cubed, and the other one is 2x cubed minus 7x squared plus 5x minus 1. I do want to mention that if you were doing this in your homework and you really didn't understand what was happening, Desmos would probably be better for visualizing it. But again, you're not going to have Desmos on your quizzes and tests and exams in this course. So worth it to learn about this thing. Now, set. This is the important moment. Before you hit table, I could hit table, and that wouldn't cost me anything. It might not be the right setup. I want to know end behavior. So when I go to set in the table here, and is your set, oh yeah, we decided our set is in the same spot as long as you're in table, right? Yesterday we couldn't find set, but it was because we weren't in the table, we were in the graph. Okay, set, start at, well, I'm going to start at 0, just not to confuse the issue. And I'm going to learn my lesson that I don't need to go too big here because my calculator doesn't like it. I'm going to go up to 1,000 and see if that's big enough to find out what I want to do. Step, though, I don't want to go 1, 2, 3, 4, 5, all the way up to 1,000. So I'm going to make the step into 10. And I think those are the settings I used yesterday and finally got it to do this end behavior thing. Exit out of there, and then I hit table. Now, these functions are very different right now. At x equals 10, the two different functions I typed in have very different values. But just go down the table for a minute. Out to, well, by the time I get to 510, do you see what's happening? One's at 2.65 times 10 to the 8th. The other one's at 2.63 times 10 to the 8th. Yes, they're still different. But can we agree that their end behavior is the same? They're heading in the same direction in a big way. And they're not super close to each other, but they are. You know, 2.65 million and 2.63 million, you know, in a larger sense, those are close now. Question. The two y's for these two functions here. Yeah, the two functions given in the question. So I'm going to go down a little farther because I do think they settle in even a little better than this once I get to 1,000. 1.94, 1.93 times 10 to the 9. So they've really settled into each other. That's not the point that these numbers are exactly the same. The point is they have the exact same end behavior. And maybe we could have predicted that when this whole question started. So What's the point? Use a calculator to show that 2x cubed can be used to model the end behavior. This is a fairly complicated function, but from an end behavior standpoint, we can just use this one, 2x cubed. And then it's easier to analyze. 2x cubed means positive x's mean big positive y's. What happens with negative x's? I hope you know, but just out of curiosity, I'm going to see if I can get my calculator to set start value 0, end set. Start value 0, end value negative 1,000. Step negative 10. Is this going to work? I haven't even tried this on this calculator to see if that's going to work. Negative 10, exit table. Oh, it worked. Yeah. So you can just make it go in the opposite direction. And what happens? They get really big, but they get really negative. Why does it get really negative when you use really big negative x values here? Power is an odd number, so when you sub in something big and negative and you do odd power to it, you get a negative number. And the fact that there's a leading coefficient of 2 doesn't change that sign at all. So these two things have the same end behavior. They both do this. Are they different in here? Yeah, they might be really different in here, but their end behavior is the same. Good? So here's the definition of these end behavior models that I'm talking about. A function g is a right-hand end behavior model if and only if its limit as x approaches infinity of f at x over g at x equals 1. What they mean is if you divided these two numbers here, f and g, look at, well, if you divide the two of them, you're going to get 1 for big x values. As the x values get big, these are pretty much going to be the same. Their limits heading towards 1 when you divide them. If a function is both a left and right end behavior model, it is simply called end behavior model. Show algebraically. So, okay, blah, 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 blah. What does all this mean? It means to prove it. Not with a calculator, but to algebraically prove that that function given is an end behavior model. What we have to do is go find the limit as x goes to infinity of f at x over g at x. And so the functions were, oh, I lost my controller here. 2x cubed minus 7x squared. Plus 5x minus 1 over 2x cubed. Oh, and I'm finding that limit as x goes to infinity. And this should seem very familiar with the weapon I used yesterday. I'm now finding limit as x approaches infinity. 2x cubed over 2x cubed. 1. Then 7 over 2x. 5 over 2x squared minus 1 over 2x cubed. I'm going to stop there. I did that very quickly because I'm presuming yesterday's went well. But if I'm wrong, now's the time to tell me. If the algebra I just did is like, whoa, 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 what are you doing there? Now's the time. Don't wait until the lesson's over. Don't wait until you're halfway through the homework. Right now, tell me if I did that. Let me just check if I did it right first. 5 halves 2x squared. Yeah, I think it's right. Question. Okay, so I was dividing each of those terms by the 2x cubed. So when I took 2x cubed and divided by 2x cubed, I got 1. When I divided 7 halves, or 7x squared by 2x cubed, the 7 halves is there. And x-wise, there was x squared and x cubed, so all that was left was 1x in the denominator. X squared canceled out of that one. In this one, only 1x canceled out, so I was left with x squared in the bottom. And here, no x is canceled out, so I was left with the whole 2x cubed in the bottom. Better? More explanation? Oh, good. We're getting some nodding. Maybe you are committed to nodding. It was just too early. Earlier, you're like, no energy yet. Can't even nod. Okay. The argument from yesterday is this is beautifully set up to find limits at infinity. One at a time. Limit as x goes to infinity of 1. I hope we beat that to death where it's like, well, if it's just a number, I know it's heading to 1. But what happens to each one of these? They're all zeros. Yeah? You got some number over some x value, and the x value is getting bigger and bigger. Just imagine even this one here. 7 over 2,000, 7 over 20,000, 7 over 20 million, 7 over 20, 100 and billion, zillion, billion, gillion. Yeah? These are all going to 0. Will they all be a little bit? Yeah, they're not going to be 0. This answer is actually 1.00000000000, as many O's as you want. 1. You know, it is, but it's heading towards 1. So what did I prove? Therefore, g at x is an end behavior model of f at x. Did I really prove that? I left one little thing out to really help this. To really be an end behavior model, it has to be true for both positive infinity and for negative infinity. So let me add the negative infinity in here as well. If I was doing positive and negative all the way along there, all that would have changed was the signs of these. Instead of being positive zeros, they might have become negative zeros. And positive and negative zeros, really, we still think of as 0. Maybe it's not 1. Maybe it's 0.9999999999999, but that doesn't really change the fact that it's heading towards 1. So I did both. Now I fixed it to do both positive and negative, because this said you've got to do it from both sides for it to be a legitimate end behavior model. Maybe it's only a left-hand behavior model. Maybe it doesn't work for the other side. Yeah. All these zeros would change. Oh no, some of these zeros would change their sign. Oh, so I implied, oh, this is going to come out to 1.0000000, and maybe that's not true. Maybe with those negative zeros in there, it comes out to 0.999999999, and I really don't care, because I'm only asking where is it headed towards. That's just figuring out, is it coming from above or is it coming from below? And this question doesn't ask about, is it coming from above or is it coming from below? It only asks, is it heading towards 1? Yeah? Other questions there? Okay, here's some more complicated ones. Really, I don't very often ask you to do that limit on a test. I ask that you know these well enough that you look at them and go, oh, I know what the end behavior model would be for these. Okay, so I'm not going to actually do the limits here. I'm just going to find a good end behavior model for this. And this is the slide you really want to pay attention to about end behavior models, because this is the kind of question that you're going to see in the homework and certainly on the test. Well, I don't know. Can you look at this? Take a second, because they tried to confuse you here. What do you think would be a good end behavior model? The simplest function I could use that would have the same end behavior as this thing. What do you like? That's a power of 5. Yeah, is that what you're saying? Yeah. Yeah, he's remembering the rules. With odd, it's like positive like this. It's negative like this. So what I'm asking then is, come up with a simpler function than this that doesn't have all these terms, maybe just one term, that would give the same end behavior as this, when we've decided that end behavior is like this. What's the simplest version I can give? Yeah. And there might be other choices, actually. But that's the one I think you should go to for now, is like, okay, just find the highest exponent and say, yes, it's going to act like this. It's going to be the same as this one. Then when they become rational functions like this, you're just going to have to think of the two pieces separately. You're going to have to say, okay, well, the numerator's going to sort of act like 2x squared. The denominator's going to sort of act like 4x cubed. So the function I can use would be 2 over x. Give that a second to make sure the algebra doesn't confuse you. What I did is I said, okay, a good end behavior model of the numerator is 2x squared. A good end behavior model of the bottom of the denominator is 4x cubed. And all I did then was divide those two. 2 over 4 reduced to, 2 over 4 reduced to 1 over 2 there. All this complicated calculus, and I can't reduce fractions. And then x squared over x cubed is just an x. Do you want to talk about that? Or is we like, okay, yeah, that we got. Good? So let's try this one then. One more. What n behavior model do you suggest for the numerator? 5x squared. What n behavior model do you suggest for the denominator? 3x squared. And if I cancel those out, here's a good n behavior model. G at x equals 5/3. This is the horizontal asymptote, right? This thing has a horizontal asymptote at 5/3. So a good n behavior model is 5/3. That's what it's going to look like out at the ends, okay? So this is really just simplifying down the stuff we've been talking about all the way along, using some complicated math to really simplify our thinking here. Do you have any questions there? Yes, thank you. I'm not sick. Don't worry. If I get 0.1% symptoms, I'm staying home to model good behavior in the middle of all this. And then we'll figure out what we're going to do later without me here. I don't know what we're going to do. But there's certain courses in this school that probably can't run without your proper teacher. I would say maybe chemistry is like that. We're not going to just walk another chemistry teacher in there, probably. You know? And if I'm away, you're going to get a very interesting lesson plan for the day, and then I'll be back. But so if you hear me cough, it's because I'm talking so much, not because I have symptoms. I saw a hand. Oh, I was going to talk about that. Maybe now's a good time to do it. I wonder, I'm watching the cases carefully. Not because I'm scared, because, you know, I don't know how you feel about COVID. That thing drops by my house, we're going to kick the crap out of it. Yeah? We're going to beat it. No problem. Yeah? I'm not really fearful of it, except I got things to do. I can't let this thing derail me. However, the province, it's doing this, right? It's crawling in towards us. Gives me the EBGBs, you know, thinking about it. But if it does hit, they're going to want us to use Microsoft Teams. So maybe sooner rather than later, we should do a test run on it. Maybe have a study session on the weekend or something like that, on a Friday night or something, and we'll all test it out and find out what the problems are, so we're not finding out the problems if we're shut down, okay? And then, yeah, if I'm symptomatic but not sick, maybe your supply teacher is just going to appear in here, and then I'm going to appear on the screen. I don't know whether you'll see me or whether you'll just hear me and you'll see my writing on the screen, and then I don't know what we'll do about questions. Maybe that's what the supply teacher will do, is they'll go, oh, there's a question here, and they'll tell me about the question, or I don't know. We'll try it, okay, if the time comes. Did I give you enough time to process this and make sure it's clear? Yeah? Last example. Show that g at x equals x is a right-hand behavior model of this. Okay, the last question I sort of glossed over the left-hand and right-hand thing. Because for polynomials and rational functions, whatever they do on the left and the right, it's a little more clear. But this thing does different things on either side. But they walk us right to it. They really tell us what to do here. They say, apparently, g at x equals x is a good n behavior model. Oh, whoops. Is a good right-hand behavior model for this function here. So let's go back to the definitions and make sure that we know how to figure out if it is an n behavior model. It said to be a right-hand behavior model, we need limit as x goes to infinity of f at x over g at x. We needed that to go to 1, it said. Essentially, it's saying we need these things to head to the same value. If they're heading towards the same value, if you divide them by each other, you'll get 1. So the f at x here is, which one am I doing? I'm doing right end. And they want x. Okay, so x plus e to the negative x over x. Let's just make sure I've copied that down. I'm doing right end. Right end behavior model of h at x, of x plus e to the negative x. Right end is x. I've got to find that limit. Now, and they were specific. They said show that it is. So they were like, show this comes out to 1. So apparently it really does come out to 1. So I'm going to use some limit laws here. And one of the limit laws says you can break a limit into 2 different limits. And I can go after this limit and this limit separately. Limits are very kind. It's like do them whatever order you want. Do the limit of one and the limit of the other and add them together afterwards if you want. And this one comes out to the nice 1 that I'm looking for. Oop. And all I'm going to do to this one to give us a chance at evaluating it is put the e to the x on the bottom. And this is the algebraic step that you have to understand to be able to handle this question. If it's e to the negative x, I can put it down in the denominator and make it e to the positive x. That's what e to the negative x is it's really dividing by e to the x. And then my job for the next few seconds is to convince you that this has to be 0. Noah. Is it good? Okay. What's that? Is this going to be easy to convince you this has to be 0? It really should be, because it's 1 over something that's getting not just big. Like 1 over x was enough. 1 over x is going to 0. But 1 over x times e to the x is getting really, really big. So this is 1 over something unbelievably big. That's heading towards 0, and I get 1. That is not a particularly tough limit. No tricks, no fancy things you have to do. You just look and go, oh, this has to go to 0. Now I'll do the left hand. Limit as x goes to negative infinity. And they said the left-hand behavior model that they suggested was e to the negative x. Right? E to the negative x left hand. Okay. And I'm going to use the same trick. I'm not going to panic here. First one is x over e to the negative x. And the next one's e to the negative x over e to the negative x. I'm going to break those into 2 limits. This one becomes x e to the x. And this one becomes 1. So now my job is to convince you this thing comes out to be 0. And at first glance, it looks like big trouble. You're like, no, this doesn't go to 0. All the ones we had before that went to 0 had a denominator. And the denominator got unbelievably big. And that told me that we were heading towards 0. And this one looks like, well, that's x e to the x. Doesn't that get big? Doesn't x e to the x get ridiculously big? Like if I've got some big x value, and I multiply it by some really big x value, I'm going to get something giant. So what's going on here that makes this that, no, this goes to 0. Don't worry, this goes to 0. Yeah, this one's going to negative infinity. And I'm making a big deal about this, and maybe you're unimpressed. You're like, yeah, I would have caught that. I can still remember a midterm where I missed this completely. I stared at it and stared at it and stared at it. It was the only question I had trouble with in the midterm. staring at it. Handed it in. No idea. I'm like, what? They must have made a mistake. You ever do that? When you handed a test and, oh, the teacher made a mistake. That one didn't work. And I got it back and go, negative infinity. E to the negative infinity would be 1 over e to the infinity. This goes to 0. And I'm going to put a big exclamation mark under that because that is a tricky little doodah in the middle there. And it sounds like I'm giving a hint for the test, and I'm not. I didn't put any of these I didn't plan any of these tricky little doodahs. I do want to mention that. Really take a look with infinities, which infinity you're putting in, because positive infinity and negative infinity are totally different ball games. Like They seem like it's the same thing. Oh, positive infinity. Yeah, negative infinity. Same thing. You couldn't be more different. You couldn't possibly be more different mathematically than positive infinity and negative infinity. Is that good? I think you'll find the homework and the test on end behavior models pretty straightforward stuff. Really not trying to bake you on this stuff. Just get a feel for them, okay?